Hello everyone, my name is Ben and welcome back to Math with Ben, and today we will be talking about derivatives. So what is exactly a derivative? Well, a derivative is simply an instantaneous rate of change. Definition: the derivative of a function is the instantaneous rate of change. There are other words for derivatives like the gradient of a function, but for this, that's more for like multivariable calculus and vector calculus. So today we will be focusing on the word derivatives. The derivative of a function is the instantaneous rate of change at a point. So how do we find this? Well, we know that the slope of any function is a change. The slope of any linear function is the change delta y, the change in the y value over the change in the x value. And so that is the derivative for any linear line, linear function, such as this one, right? If we have like the graph of y equals x, if we want to go from 0 to like 4 minus 0 divided by 4 minus 0 is equal to 1. And we can see that in the graph, or in the equation, right? We have y equals mx plus b. We can see that m in this case, which is the slope, is just 1 and b is 0. So y equals 1x plus 0. And that's just the equation of this function. The derivative, the point of the derivative, is to find the slope of more complicated functions, right? For this, not necessarily a slope. Again, it's the rate of change. Okay, so slope was a bad example. Let's say we have the graph of x squared, and we want to find like the instantaneous rate of change. How can we do that? Well, last time we talked about limits. So the limit, there is a limit definition of a derivative that allows you to find the derivative of any function using this definition. And this is what it is. The limit as h approaches 0 of f of x plus h minus f of x divided by h. What is x in this case and what is h? Well, let's get into that. If we want to draw our graph like a little bigger here, let me just super big. All right. So this initial position will be f of x. And this right here will be f of x plus h, where this initial value here is x and this secondary value here is x plus h, where the difference between those 2 points, let me do a different color, this difference here is h. So all that this limit is saying, right, what we said last time is the limit is saying as some variable approaches a certain value, what does that function become? And we can see here the variable in this case, oops, I forgot a 0 here. The variable in this case is h, and it's saying as the difference between 2 points approaches 0, what is the change in y position, right? So here, this is the second y, so like I said, that this f of x plus h is the second y value. In this case, we're doing, delta y, change in y. And the first one is the first y value, right? First y. So this is y1 minus y2 over the change in x, right? H is just the change in x. So x1, the difference between x, oh, oopsies, I made a mistake here. y2 minus y1, x2 minus x1. And so this x2 minus x1 in this case is just h, right? It's the difference between f of x plus h and x, right? And it's the difference between x plus h and x, right? X plus h minus x is just h. Let's do a quick example with this definition. We're doing x squared in this case, right? F of x equals x squared. So we'll take the limit as h approaches 0 of x squared, x plus h squared, right? Because f of x is x squared. So f of x plus h is x plus h squared minus x squared over h. And so we'll expand this, and this is equal to the limit as h approaches 0 of x squared plus 2hx plus h squared minus x squared all over h. And what we can do is we can cancel those because they're the same, right? And now we have that is equal to the limit as h approaches 0 of 2hx plus h squared over h. And we have a problem, right? Because as we stated in the last video, you can't divide by 0. It's a felony offense up to 10 years in federal prison. So in this case, how will we determine this limit? Well, we can actually factor out an h on the top, as you might have seen already. You might not have, that's okay. So the limit as h approaches 0 of h times 2x plus h over h. And then these h's will cancel. And so we get the limit as, not x, h approaches 0 of 2x plus h is equal to 2x plus 0, which is equal to 2x. So the derivative of x squared is 2x. And there's a much easier way to do this. So let's get into the notation. There's a couple of different notations we can use for derivatives, and you can choose whatever you like. In some cases, it's easier to use the one Leibniz created. So we'll go over that one first. Leibniz was a mathematician sometime in the 1700s, I don't remember when, who invented calculus at the same time as Isaac Newton. They invented it separately, but they did it at the same time. So Leibniz's notation of a derivative is dy dx. The derivative of the function with respect to x. So derivative of y with respect to x, where y is the function. This is the same as df of x, the derivative of f of x with respect dx, with respect to x. This notation is a little complicated. All it's saying is that the derivative at this point, or not at this point, the derivative of this function f of x with respect to x. And that's, so in this case, we can use our example where we know that the derivative of x squared with respect to x is equal to 2x. Let's go over Newton's notation now. Newton's notation is not commonly used. It's used sometimes in physics and differential equations because it's a lot less complicated. It is just y dot. So we can do or f of x dot. You see how it's it can get it's weird look, it's strange looking. I don't like it. I don't ever use it. I prefer Leibniz's. There's also y prime or f prime of x. You can use those two, especially in early calculus. But I think Leibniz's notation is the best, and I suggest that you use it. And so now we can get into more rules about derivatives. Rules. I'll do it in pink. So we have a list of basic functions we can take derivatives of and what their derivatives are. So the first one we'll do is the derivative of a constant, d dx, or d dx of c, where c is some constant. This is equal to 0. The derivative of any constant with respect to any variable is equal to 0, and we can graph this out and show why. We can see here, right where this is, y equals c, that there's no change in the y ever. Right, so the change with respect to x, if this is an xy coordinate system, there's no change. So it's just 0. The next one we can do is the derivative of x, dx, and this is equal to 1. Not because it's a fraction. A derivative notation is not a fraction and should not be used as such. But dx is 1, as we showed this already, right? We showed that the slope or the change in y with respect to x of y equals x is 1. We already showed this. So we don't need to do it again. In fact, we'll practice actually using the limit definition of a derivative. So the limit as h approaches 0 of x plus h minus x divided by h, right? And so we'll cancel these, and this is equal to h over h, which is equal to 1. And that's pretty simple. We'll number these in pink. 2, 3. The third one is when some variable is multiplied by a function. When some constant is multiplied by a function. So if we have dx of some constant c multiplied by f of x, this is equal to c times the derivative of f of x with respect to x. Pretty simple. You can just, move the constant over here. Next, 4 is when you're adding derivatives. So if we have the derivative with respect to x of functions that are being added, say f of x plus g of x, this is equal to the derivative of f of x with respect to x plus the derivative of g of x with respect to x. Once again, they're not too complicated. These are just rules. As a math student, you will eventually just memorize. now we have what's called the product rule. There's a name for this one. When two functions are being multiplied and we want to take their derivative, dx of f of x times g of x, that's equal to the derivative of f of x with respect to x times g of x plus f of x times the derivative of g of x. And in this case, I think I'll start using some simpler notation for you. So this is equal to f prime g plus g prime f. Right, that's that same notation that I used here. And it can be useful when you start having to take a lot of derivatives of things. And so this next one I will also do in this new notation, because this one is especially complicated. If we want to take, I'm going to stop writing the full g and f of x. If we want to take the derivative with respect to x of f over g, where f and g are both functions of x, that is equal to f prime g minus f g prime, all divided by g squared. So that's, a little more complicated, and doing problems with this one is hard. So why don't we do one right now? Let's take the derivative of 2x plus 3 over x squared. dx. So first, this is f and this is g. Always helps to label which function is which. So the derivative of 2x, let's figure this out. Well, we know the derivative of a constant 3 is going to be 0. Okay, so we can start by saying that. Let's write out, actually, what our f is, what our g is, what our f prime is, and what our g prime is. So what is our f? Well, our f is 2x plus 3. And what is our g? Our g is x squared. What is our f prime of x? Well, our x prime of x, this is what we were just doing. We know that the derivative of any constant, so 3 is 0, so plus 0. And the derivative of 2x, like we said, if you have any constant, if you have any x, if you're taking the derivative of x, it's just the variable that's in front of it. So if in this case we had a 2 here, oops, not there, then this would be 2, right? We know just that if you are taking the derivative of any constant multiplied by x, it's just going to be the constant in front of that x. So this is going to be 2. And we already figured out the derivative of x squared, and that's going to be 2x. So we have our f prime and g prime here, and also our g prime. So when we're doing this, I'm going to erase this and just do it down here. So dx of 2x plus 3 divided by x squared is going to be equal to f prime g, so 2 times x squared minus g prime f, 2x times 2x plus 3, all divided by x squared, g squared, right? And that's going to be equal to 2x squared minus 4x squared plus, minus 6x, all over x to the fourth, which is that is going to be equal to negative 2x squared minus 6x over x to the fourth. We can take out an x and factor, and we can get minus, that's going to be equal to minus 2x minus 6 divided by x cubed. And that is going to be our final derivative. And so we just did it, right? It's a little bit complicated and requires some decent algebra. But, you know, if you work on your algebra and practice your algebra, you can get it done pretty well. Next, the next derivative we will do is, this is a very important derivative that you will be using the rest of your math career, however long that may be. And all it says is that the derivative with respect to x of some x to the n, where n is any variable, or x is any number, is equal to n times x to the n minus 1. That's all it is, that simple rule. So let's do this with our example earlier, which will be much easier than using the limit definition. X squared, right? So n in this case is 2, so if we take the derivative of this, it's going to be equal to n is 2, so 2 times x times the 2 minus 1, and that's equal to 2x. See how much quicker that was than using the limit definition? What if we had like 15x to the third? Right? If we wanted to take the derivative of this, d dx, that's going to be equal to, well, 3 times 15 is equal to 45, times x, 3 minus 1, is equal to 45 x squared. And see how that like scary looking derivative is so simple and so easy just using the power rule. That's all the derivative rules I'm going to go over today. There's many more, and I will post them on the Instagram I created at MathWBen on Instagram. I will post a photo of the derivative rules on there along with an announcement that this video has been released. But there's one more thing I would like to go over, and that's what's called L'Hopital's rule. I think that's where the hat goes. I'm not sure. It's French, so it's stupid. But I'm just kidding. L'Hopital's rule, we're going back to this idea of limits. L'Hopital's rule is used on limits. So let's do an example here. Where the limit ends up being 0 over 0 or infinity over infinity. So let's do one where x is approaching 0. And let's say we have 3x to the fourth plus x over 2 minus x. Oh, not 2 minus x. That was bad. Minus x. So let's plug in and see what we get. Well, we get 3 times 0 to the fourth plus 0, all divided by 0, and that's going to be equal to 0 plus 0 over 0, which is equal to 0 over 0. And we ran into an inconclusive answer, right? This doesn't help us in any way. It's not allowed. 0 over 0. That's not a thing, right? So what we have to do is we have to LHOP. I'm turning it into a verb. What all L'Hopital's rule states is that if you run into a limit, let's write it down. If you run into a limit that has a value of infinity over infinity or 0 over 0, you are to take the derivative of the top and the bottom, and redo the limit. So in our example here, let's take the derivative and see what happens. Now, I know that it's a quotient, but we won't be using the quotient rule. We will simply be taking the derivative at the top and putting it over the derivative at the bottom. So the derivative at the top, let's use our power rule here. Let's do 3 times 4, bring the 4 down, which is 12, and then subtract 1 from 4, so we get 12x to the third. We know that the derivative of x is 1, and we know that the derivative again of x is 1, which is equal to the limit as x approaches 0 of 12x cubed plus 1. And then we can plug in, because right, like I said in the limits video, this is just a polynomial, and any polynomial you have, you can just plug in 0, and this is equal to 12 times 0 cubed plus 1, which is equal to 1. And that is the answer of this limit. Nothing has changed. It's the same limit, just we've taken the derivative. And that's all LHOP rule, all L'Hopital's rule is. If you'd like me to post practice problems, again, let me know. The reason I didn't put L'Hopital's rule in the limit video is because you needed to know how to take derivatives for it. I will post a derivative sheet on the Instagram. Thank you all for watching. Thanks for watching. I'm Ben, and this has been Math with Ben. Next time, I will teach you about basics of integrals and the fundamental theorem of calculus. Thank you, and have a good rest of your night.